Have you ever just watched a ball roll down a hill? I mean, it seems like the simplest thing in the world, right? But the physics behind it, well, that's surprisingly deep. It's this beautiful dance between moving forward and spinning, and that dance is what determines everything. So today, we're going to settle it. We're going to stage a race to find the ultimate champion of the ramp.
So, here's the puzzle we're tackling. You've got 3 contestants, a hollow ring, a solid cylinder, and a solid sphere. Let's say they all have the exact same mass and the same radius. We put them at the top of a ramp, hold them steady, and let them go. Which one reaches the bottom first? Go ahead, make a prediction. Lock it in. Let's see if your intuition is right.
All right, so what's our game plan? First up, we're going to lay down the rules of the road by defining pure rolling. Then we'll get into the real heart of the matter, energy, because that's the ultimate deciding factor. After we crown our champion, we're going to bust a few common physics myths about rolling. And to top it all off, I'll show you a seriously cool shortcut that the pros use to make these problems way easier.
Okay, let's get started with the absolute foundation for our race. We need to understand the rules of pure rolling. This is what physicists mean when they say something is rolling without slipping, and it's a really specific, really important condition.
So, what's the big difference here? Well, on the left, you've got slipping. Think of a car tire skidding on an icy road. The forward speed, v, just isn't matching up with its spin, omega. It's chaotic. But on the right, that's our ideal competitor, pure rolling. Think of a bike tire gripping dry pavement. The forward motion and the spin are in perfect harmony. In fact, the forward speed v is exactly equal to its radius times its rotational speed, omega. That's the golden rule.
Now this leads to a pretty mind-bending idea. For an object to be in pure rolling, the single tiny point that's touching the ground has to be, well, completely still. For just a split second, it has zero velocity. So wait a minute, how can a point on a moving wheel be standing still? Let's break that down visually.
This image explains it all. First, just imagine the wheel moving forward without spinning. That's pure translation. Every single point on it is moving forward with the same velocity. Now imagine it's just spinning in place, pure rotation. The top moves forward, but the bottom actually moves backward. Okay, now let's combine them. Look at the very bottom point. The forward motion and the backward rotation perfectly cancel each other out. Boom, zero velocity. And at the top, they add together, making the top of the wheel move at twice the speed of the center. Wild, right? That's pure rolling.
So all of that amazing complexity boils down to this one simple, incredibly powerful equation. The speed of the center of mass equals the radius times the angular velocity. Remember this one. This is the master equation for any object that's rolling without slipping.
Okay, we have our rules. Now let's open up our physics toolbox and talk about the real deciding factor in this race, energy. How each of our objects manages its energy budget is going to determine who wins.
So what actually gets an object spinning as it goes down a ramp? Well, gravity is pulling it down, sure. But look at that other force, static friction, pointing up the ramp. It seems a little weird, but that friction is the unsung hero here. It grabs onto the surface and provides the twist, the torque that forces the object to start rotating. Without static friction, everything would just slide.
And this is the real secret to our race. Think about a simple block sliding down a ramp. It only has one kind of kinetic energy, the energy of moving from point A to point B. That's called translational energy. But our rolling objects are more complicated. They have 2 jobs. They have to move forward and they have to spin. So they have both translational and rotational kinetic energy. And here's what that looks like as an equation. The total kinetic energy is made of 2 parts. First, the familiar 1/2 mv squared for the energy of moving forward. And then there's a new term, 1/2 I omega squared for the energy of spinning. That letter I is called the moment of inertia. You can think of it as an object's rotational stubbornness, how much it resists being spun. And the crucial thing is, it depends entirely on the object's shape. This is the key.
All right, all the pieces are on the board. We've got the rules of pure rolling. We've got our energy equation. It's time. Let's line up our racers at the starting line and finally figure out who wins this thing.
We're going to solve this using one of the most powerful ideas in all of physics, the law of conservation of energy. At the top of the ramp, all the energy is stored up as potential energy, mgh. As the object rolls down, that potential energy gets converted or spent on kinetic energy. But remember, it has to be spent on 2 things, moving forward and spinning.
Okay, let's walk through the math here. Don't worry, it's not too bad. In step 1, we just plug in our rule for pure rolling and a general form for that moment of inertia.
Now look what happens in step 2. The mass m is in every single term. That means we can cancel it out completely. And that is a huge insight. It means the mass of the racers doesn't matter one bit. After we clean up the algebra, we get this beautiful final formula for acceleration. And you can see the winner is decided only by gravity, the angle of the ramp, and that shape factor, k²/r².
And here is the grand finale. This table puts it all together. Just look at that k²/r² column. The ring, with all its mass on the outside, has the highest value, which means it has the lowest acceleration. The solid sphere, with its mass packed in close to the center, has the smallest k²/r² value, which gives it the highest acceleration. And the cylinder, as you might guess, is right there in the middle.
And the winner is the solid sphere. It takes the gold. Why? Because it's the easiest one to get spinning. It has the lowest rotational stubbornness. That means it wastes the least amount of its energy budget on rotating and can spend more of that precious energy on what really matters in a race, moving forward. That's why it accelerates the fastest.
So we've crowned our champion, but now let's take a minute to tackle some of the common myths and tricky questions about rolling. These are the things that often trip people up.
Okay, first question. We said that static friction is absolutely essential to make the object roll in the first place. But forces do work. They transfer energy when they act over a distance. So, does that friction force do any work here? Amazingly, the answer is no, it does zero net work. As the quote explains, you can think of it in two parts. The negative work it does fighting the forward motion is perfectly balanced out by the positive work it does creating the rotation. The net effect on the energy is zero. Or, here's an even simpler way to think about it. Work is force times distance. Since the point where the force of friction is applied is instantaneously at rest, it doesn't move through any distance. No distance, no work.
All right, next up, let's imagine a different race. This time, it's our rolling sphere on a normal ramp versus an identical sphere that's just sliding down a completely frictionless, icy ramp. No rotation at all. Who gets to the bottom faster?
The slipping object wins, and it's not even a close race. It all goes back to that energy budget. The slipping object doesn't have to pay the energy tax of spinning. 100% of its initial potential energy gets converted directly into forward motion. So for the same starting height, it will always have a much higher final velocity than any object that has to split its energy on rolling.
Okay, to wrap things up, I want to show you a really powerful shortcut that physicists use to analyze these kinds of problems. It's called the Instantaneous Axis of Rotation, or IAOR, and it's a real pro move for looking at this motion in a whole new light. So, what is the IOR? It's simply the point on any moving, rotating object that happens to have zero velocity at one specific instant. And here's the magic trick. For that one moment, you can pretend that the object's entire complex motion is actually just a simple, pure rotation around that single point.
So where is this magic axis for our rolling objects? Well, we already found it. It's the point of contact with the ground. We spent all that time proving it has zero velocity. The shortcut is realizing that you can now think of the entire wheel as just a big pinwheel pivoting around that one spot on the ground. It can make calculating the velocity of any other point on the wheel incredibly simple.
And that brings us to one last thought to leave you with. Imagine you're playing pool. You can hit the cue ball low to give it backspin, or hit it dead center to make it slide for a bit. But there is one single, perfect spot you can hit it that will cause it to roll purely, without any slipping from the very first instant it struck. Now that you know all about forces, torque, and energy, where do you think that spot is?